Hi folks, today we are going to talk about the chain rule, which is a technique to differentiate functions that are composed of other functions. We are going to see lots of examples and then we're going to see how we can use the chain rule to give the derivative of exponential functions. We already know the derivative of the exponential function with base e, but now we are going to see how we can get the derivative of exponential functions for any base. So let's consider this function square root of x squared plus 2x minus 7. And it is composed of two other functions. We can say that f of x is equal to square root of x. And then if g of x is equal to x squared plus 2x minus 7, then if we compose the two functions, so f of g of x is equal to f of x squared plus 2x minus 7. So what the function f does, it takes its argument and then it takes the square root of the argument. So our argument now is x squared plus 2x minus 7. So what f is going to do is it's going to take the square root of that argument. So we're going to have square root of x squared plus 2x minus 7. So this function is composed of two other functions, and the chain rule, it helps us to differentiate um, uh, composite functions. So we say that the function f is the outer function, and the function g is the inner function. So what the chain rule tells us is if we have two functions f and g, and then if we compose f of g of x, then the derivative of that function is going to be f prime of g of x times g prime of x. So in other words, it means that we are evaluating f prime at g of x, and then we are multiplying by the derivative of the inner function. So let's take a look at some examples. Let's evaluate the derivative of this function 2x plus 3 raised to power 5. So my outer function is going to be f of x equals x raised to power 5. And my inner function is going to be g of x equals to 2x plus 3. Well, I'm going to write here on the side what the derivative of a composite function is. So it's f prime evaluated at g of x times g prime of x. So we need f prime and we need g prime. And also we need f prime evaluated at g of x. So let's do one step at a time. So differentiating f gives us f prime of x is equal to 5 times x raised to power 4. And differentiating g of x gives me g prime of x equal to 2. Because we have polynomials in both cases and we do know how to differentiate polynomials. Now, the derivative of f of g of x, like I said, it's going to be f prime evaluated at g of x. So let's compose f prime with g of x. F prime of g of x is going to be equal to f prime of g of x, which is 2x plus 3. So let's take a look at f prime. So f prime takes an argument x, and then it raises this argument to power 4, sorry, and multiplies by 5. So my argument now is 2x plus 3. So what f prime is going to do is it's going to take the argument and raise to power 4 and multiply by 5. So f prime of g of x is this, and g prime of x is 2. So we are ready to give the derivative of the function. So dx of 2x plus 3 raised to power 5 is going to be equal to 5 times 2x plus 3 raised to power 4 times 2, which is equal to 10 times 2x plus 3 raised to power 4. And then we have the same information in the slide, but I typed. Now let's evaluate the derivative of cosine of half of x raised to power 4. So my outer function in this case is going to be f of x equals cosine of x. And my inner function is going to be half times x to the fourth. Well, we do know how to differentiate cosine. We saw this in one of the previous videos. So f prime of x is minus sine of x. And because in the function g we have a power, we're going to apply the power rule. So it's going to be 4 times half times x raised to power 3. And that is equal to x cubed. So once again, the derivative of a composite function is equal to f prime of g of x times g prime of x. So I already have f prime and I already have g prime, but I need f prime of g of x. So f prime of g of x is going to be f prime of half times x raised to power 4. So what my function f prime does to an argument x is it takes the minus sign of that argument. So f prime of this argument is going to be minus sign of that argument. So now we are ready to give the derivative of f of g of x. So the derivative of cosine of half times x to the fourth is going to be equal to minus sine of half times x to the fourth times the derivative of the inner function, which is 2x cubed. And once again, we have the same information, but now it's typed. Now let's evaluate the derivative of this function, square root of 5 times e to the x plus 4 times x cubed. So my outer function, once again, is going to be f of x equals the square root of x. My inner function is going to be 5e to the x plus 4x cubed. So f prime of x, well, actually, let me first rewrite this function as x raised to power half. So f prime of x is going to be half times x raised to minus half, which we can rewrite as 1 over 2 square root of x. So now let's differentiate g. So g prime of x is going to be 5 times e to the x, because the derivative of e to the x is e to the x itself, plus the derivative of the second term is going to be 12x squared. Now to give the derivative of the composition of those two functions, we need f prime of g of x, which is f prime of 5e to the x plus 4x cubed. So what f prime does to an argument x is it takes half, and then in the denominator, it multiplies by the square root of that argument. So what f prime is going to do to this argument is it's going to take half And in the denominator, it's going to multiply by the square root of the argument. So 5e to the x plus 4x cubed. So now the derivative of our function is going to be so this part is the outer function, the derivative of the outer function evaluated at the inner function. Now we multiply by the derivative of the inner function. So we're going to multiply by g prime. So here's the derivative of g prime, and I'm going to write like this. So it's going to be 5 times e to the x plus 12x squared. And that's what we have written in the slide. So here, instead of writing this as a denominator with the square root, we have the power minus half. Now let's evaluate tangent square of x, the derivative of tangent squared of x. So notice that tangent squared of x is the same thing as tangent of x times tangent of x. Well, so it's going to be tangent of x raised to power 2. So my outer function is going to be f of x equals x squared, and my inner function is going to be tangent of x. So the derivative of x squared is 2x, and the derivative of tangent, so g prime of x, is secant squared of x. So this means that the derivative, I'm going to do it a little bit faster than I was doing the previous examples because we have seen quite a few already. So it's the derivative of the outer function evaluated at the inner function. So it's going to be 2, but instead of writing 2x, I'm going to have 2 tangent of x times the derivative of the inner function, so secant squared of x. So once again, this first part here is the derivative evaluated at the inner function, and the second part is the derivative of the inner function, which is what we have in this slide. So we have to think that to give the derivative of a composite function, we are thinking derivative of the outer function evaluated at the inner function times the derivative of the inner function, and then that's what gives us. Let's consider one more example. So now, not only we are going to consider the chain rule, but notice that we have a product here. So we also have to apply the product rule in this example. We're going to see how to apply this. So my outer function is going to be f of x equals x raised to power 4. And my inner function is going to be g of x equals 1 plus x sine of x. So the derivative of my outer function is 4x cubed, and the derivative of my inner function, so derivative of constant is 0. And now because I have a product here, I have to apply the product rule. So I'm gonna have, I'm gonna leave the first term alone and multiply by the derivative of the second term. Now I'm going to differentiate the first term, so derivative of x is 1. And I'm going to leave the second term alone, so sine of x. Now the derivative of 1 plus x sine of x raised to power 4. It's going to be the derivative of the outer function evaluated at the inner function. So it's going to be 4 times 1 plus x sine x cubed times the derivative of the inner function, which is x cosine x plus sine x. So notice, notice that I use parentheses here because I have to multiply the first part by both terms. So if I don't put parentheses, it would mean that I was only multiplying by the first term. So here we have the same information that we had in the previous slide, but it's typed. Let's move to another example. We already have the example and the solution in the same slide. So we are going to consider the derivative of this function, cotangent of a fraction. So because we have a fraction, we are going to apply the quotient rule. So my outer function is going to be cotangent of x, and my inner function is going to be the fraction. So the derivative of the composition of those two functions is going to be um, the derivative of the outer function. So derivative of cotangent is minus cosecant squared evaluated at the inner function. So minus cosecant squared evaluated at the inner function. So this is the inner function times the derivative of the inner function. So to give the derivative of this inner function, we have to apply the quotient rule because we have a fraction. So we repeat the first part, and then to differentiate the second part, we use the quotient rule. So it's going to be low d high. So this is low, sine of x is low. D high is the derivative of the numerator, which is a polynomial. So we do know how to differentiate polynomials. It's going to be 2x minus 2 minus high d low. So this is the numerator, this is high, and then d low, derivative of the denominator, derivative of sine is cosine, over the square of the denominator, so over sine squared of x. Let's consider one more example. Now my outer function. So before we actually take a look at this example, I'm going to point out that this is the inner function. This exponent is the inner function. And within that inner function, we also have a composition of functions. So we are going to apply the chain rule twice. So let's solve this. My outer function is f of x equals e to the x, and my inner function is square root of 9x squared plus 1. So the derivative of e to square root of 9x squared plus 1 is going to be equal to the derivative of the outer function. So the derivative of e to the x is e to the x itself, but it's going to be the derivative of the outer function evaluated at the inner function. So it's going to be e raised to square root of 9x squared plus 1 times the derivative of the inner function. So times the derivative of square root of 9x squared plus 1. So notice that here, once again, we have a composition of functions. So let me call the outer function now h of x equals square root of x, which is equal to x raised to power half. And then let me call I of x the inner function. And it's going to be the polynomial 9x squared plus 1. So we're going to have the derivative of e to 9x squared plus 1 square root of that. The derivative of that is going to be the first term we are simply going to repeat. And now we differentiate the second term. Um, but once again, we have a composition of functions here. So this is the composition of functions. So it's going to be the derivative of the outer function evaluated at the inner function. So the outer function is h, the inner function is I. So the derivative of x raised to half is half times the square root of x. But instead of evaluating square root of x, we're going to evaluate at the inner function. So it's going to be square root of 9x squared plus 1. And that multiplied by the derivative of the inner function. So the inner function is a polynomial. We do know how to differentiate polynomials. This is going to be 18x. And that's the same information that we have in this slide. Well, but actually, I found a typo. We do not have this exponent 2 here. So this is wrong. So it should be 18x and not 18x squared. Now we are going to see how we can use the chain rule to give the derivative of exponential functions for a generic base b. So we're telling you in the slide that the derivative of a function b to the x is going to be b to the x times ln of b. And we are going to use the properties of natural log and exponential to explain why this is true. So I can rewrite b to the x as e raised to ln of b to the x. So why is this true? Because exponential and logarithmic and log are inverse functions of each other, so they can cancel each other, and we would be left with b to the x simply. So if I want to differentiate b to the x, that's the same thing as differentiating e raised to ln of b to the x. Now we are going to apply the chain rule on the right-hand side of this equation to give the derivative of this function. So this is going to be my outer function. This is going to be my inner function. So the derivative of the outer function is going to be e, but we are going to evaluate at the inner function, so ln of b to the x times the derivative of the inner function. So the dx of ln of b to the x. Well, e and ln, they are inverse functions of each other, so they cancel each other. So this is b to the x. And now here we are going to use a property of natural log that tells me that if I have an exponent, I can bring it to the front. So this is going to be the derivative of x times ln of b. Well, keep in mind that ln of b is a constant. So if we are differentiating x times a constant, the derivative is going to be the constant. So this gives me b to the x, which was the first part. And then the derivative of x times ln of b is simply ln of b. So this is the derivative of an exponential function of the form b to the x. So let's use what we just learned to evaluate the derivative of this function. So in this example, my outer function is going to be 2 to the x, and my inner function is going to be the exponent, which is a polynomial minus x squared plus 2x plus 4. So the derivative of that function is going to be the derivative of the outer function evaluated at the inner function. So it's going to be 2. Instead of being 2 to the x, is going to be 2 raised to minus x squared plus 2x plus 4 times ln of the base, which is 2. And now we multiply by the derivative of the inner function. The inner function is a polynomial. So the derivative of that is minus 2x plus 2. And that's the information that we have in this slide, but typed. And this was the last example for this video. I'll see you next time.